Hi, I'm John Turner. I'm going to talk about how 3D movies are made. First, we should talk a little about how 3D vision works. When you look at an object, each eye is looking along a different line of sight. And so each eye sees a different perspective on whatever you're looking at because of this different angle. This is called parallax viewing. Well, your brain interprets that as a 3D view. And so how could one reconstruct a 3D view? Well, if you could take a picture from each view, and then when viewing the two pictures, the right eye and left eye picture, separate the images so that the right eye only sees the right eye view and the left eye sees only the left eye image, it would look three-dimensional. In fact, this is the way the old Viewmasters worked. Each picture in the sequence was photographed with two cameras from slightly different positions. And then when you held the system to your eye, the right eye saw the right eye picture, the left eye saw the left eye picture. And they're not identical. They wouldn't exactly overlap. So they looked very realistic. In fact, to me, they looked almost super 3D, more than 3D. I suspect that's because the separation of the cameras was a little more than maybe my eye spacing, and so it exaggerated the parallax just slightly. Anyway, that's a way of recreating from two-dimensional images a three-dimensional perspective. Now, how could that be done with movies? Well, suppose you could do something like this. Suppose you had a special projector that in alternate frames projected a left eye view, then a right eye view, left eye view and right eye view. So the first frame comes out. If you had a way to cause that image to only get to the left eye and not to the right eye. And then in the second frame, the right eye image comes out, and if you had a way to get that one only to the right eye and be blocked by the left eye. And then the third and fourth and so on. And so as time progresses, each eye would alternately see very quickly the image that it should see, and the other eye would not. That would be a way to create a three-dimensional effect in a movie. Well, in effect, that's how it's done. How do they go about doing such magic? Okay, well, to talk about that, we need to talk about polarization of light, because that's one of the most effective techniques that's used these days to do this. This sketch shows the concept of plane polarized light. This is the electric field represented as a vibrating electric vector of light. And if that vector vibrates in a single plane, as shown here, then if you could actually see that little electric vector as it comes through your eye, you would see it vibrate to the right and then back to the left, and to the right and to the left. And that would be called a linearly polarized light, and we might call that a 0-degree polarization angle. Alternatively, if the vibration is rotated and is going vertically up and down, then we would call that linearly polarized at 90 degrees. Polarizing filters actually pass or block linearly polarized light. So if you had a pair of glasses, as shown here, with a horizontal filter on the left one and a vertical filter on the right one, then this 0-degree polarized beam would pass through the left image, would get blocked by the right image. On the other hand, the vertical polarized beam would pass through the left image and get blocked by the right image. So one possibility is to project the left image frames with horizontal polarization, the right image frames with vertical polarization, and then match up the blocking filters so that each eye only sees the proper image. And in fact, most descriptions of 3D movies describe it that very way. This was actually the way that 3D movies were made some years ago. But there were problems with this. It was not as high quality as one would like for a couple of reasons. One is that you can see here that if you tilted your head, the plane of blockage would not be perfectly aligned with the vertical and horizontal anymore. And so some of the left eye image would bleed through the right lens, the right eye image would bleed through to the left lens. And so if you tilted your head, it destroyed the quality a bit. Another reason is that these images have to be reflected off of a screen at the movie theater. And when you have polarized light coming into a screen and then reflecting off, the state of polarization is disrupted a bit. And plane polarized light is disrupted considerably for certain angles. So further work went forward to try to improve this scheme. And in order to understand how it's actually done, we have to go a little bit further into talking about polarization. So let's continue this a little further. Suppose I have two plane polarized waves, one vertical and one horizontal, propagating at the same time. If you looked at the resultant polarization vector, again, it's oscillating. It's 0, then it grows to a maximum, then it goes back to 0. But the resultant of that horizontal and vertical is now going to be along a 45-degree angle. So in this case, these two components of the electric vector produce a 45-degree plane of polarization as shown here. And if you could actually see it, would be oscillating at 45 plus and minus. Suppose you took one of these polarized components and phase shifted it a half wavelength, forward or backward. In this case, I've shifted the vertical polarized beam back 1/2 wavelength. Now, if you look at the resultant, it still oscillates from 0 to a maximum to 0, but this time it's vibrating along a minus 45-degree angle. So by a half-wave shift, phase shift, we've rotated the plane of polarization from plus 45 to minus 45, or in other words, by 90 degrees. Okay, that's one important feature we want to keep in mind. And now there's one more step that we have to look at before we can talk about how the real movies are done today. What if instead of a half wave, we said, let's put a quarter of a wave shift? What does that do? Okay, this sketch on the left shows the vertical and horizontal plane polarized beams, but with, instead of a half shift of wavelength, we put a fourth of a wavelength shift. And now if you look at that electric vector as it passes through a screen here, we see the vector first acting out to the left, then a little later acting vertically up, then a little later acting out to the right, and so forth. In other words, as it passes along in time, the resultant vector is rotating around a circle, and it's actually staying constant in magnitude. So it rotates, in this case, in a clockwise direction. So we call that clockwise or left-handed circular polarization. So we say that's a circular polarized light state. Well, you could have quarter wave shifted in the opposite direction, and you get almost the same thing. The only difference now is as time progresses and the beam moves forward, the direction of apparent rotation of that vector is the other way. And we would call that right-handed circular polarization. So a quarter wave shift produces either left-handed or right-handed circular polarized light. Okay, now we can talk about how to use that in making 3D movies. Suppose I have images for the left eye that are left-handed circular polarized, as shown by this wave set, and the right eye images are circularly polarized counterclockwise or right-handed, as shown by this wave set. Now suppose coming off the screen, this is the left and right-handed circular polarized beams, and they each contain left and right eye image perspectives. Now suppose just before they get to your eye, we do something, add another quarter wave shift to each beam. If you do that, that makes basically a half wave shift on one of them and 0 wave shift on the other, so that they become plane polarized again. So this one would now be plane polarized at plus 45 degrees, and this one would be plane polarized at minus 45 degrees. Now, if I put some polarizing filters in front of your eyes so that the right eye blocks the left eye polarized beam and the left eye filter blocks the right eye polarized beam, then again I would see the proper images in each eye. Now, that's exactly what's done in contemporary 3D movies. The left eye images are circularly polarized in one direction, the right eye images are circularly polarized in the opposite direction, as shown here. It turns out that one can buy plastic sheets that produce a quarter wave shift, and those can be laminated onto polarizing filters so that your glass lens is a 2-layer construction. The first layer is a quarter wave shift. The second layer is a polarized filter, and the direction of those polarizing filters can be made 90 degrees from one another in any angle you want. So if the polarized glasses are constructed this way, then the left eye image and the right eye image will come through the quarter wave plates and now be linear polarized, so that only the right eye image gets through the right lens and only the left eye image gets through the left ends, and the alternates are blocked. Okay, that looks like a complicated way to achieve the same thing that we did with simple plane polarization. Why is this better? Well, a couple of reasons. One is that the circular polarized light is not sensitive to the tilt angle of your head. In other words, if this is circularly polarized, this quarter wave shift works no matter what the tilt angle. So now there's no more tilt sensitivity with this scheme. So the quality is very good. And secondly, the reflection of these polarized beams off of the movie screen, when they come in and reflect off, the state of circular polarization is retained much better than the state of a plane polarized beam. So basically the quality of the polarization is closer to what it should be even after reflection off of a movie screen. So that's basically how the current movies work. This is a little more detailed than perhaps most people would want to know, but if you're a little bit technical, this is a little more accurate than most things you'll find online that describe these movies. So to wrap up here, let me just make a few more observations. So to summarize, the left and right eye images are projected in alternate frames. For example, the left eye view might be the even frames, the right eye view in the odd frames. And then some high-speed electronic polarizing optics make one set left circular polarized and the other set right circular polarized after they come out of the projector. Your polarizing glasses then produce an extra quarter wave phase shift before the images get to your eye, and then the final layer of your glasses are polarizing filters which block or pass every other frame depending on which eye and the orientation. And it's done such that each eye sees a proper perspective image. And you might note that each eye is going to see half the total frame rate. So if the even images are coming to the left eye and the odd images to the right, if you had a frame rate of 60 frames per second, each eye is seeing basically a 30 frame rate per second. But the frame rates are high enough that you don't notice that each eye sees an alternate frame in time. So it works just fine. Just a couple of other observations. The glasses are not reversible. So if you rotated them around such that each eye sees the other eye view, for example, you could spin them around so your left eye is looking through the right eye lens and vice versa. Then your left eye would see what normally your right eye sees and vice versa. And you can do that in the theater. It's kind of neat to do it, but your brain is not trained to interpret that result as three-dimensional. So if you do that, it won't look three-dimensional. The other thing you could do with the glasses is flip them over to look through them from the outside surface. But if you do that, the quarter wave phase shift doesn't occur before the images hit the polarizers. And actually both images will partly bleed through both lenses. And so again, your brain would not see that as three-dimensional. In fact, that's a little bit like looking at the screen without the glasses on at all. Finally, if you want to do a little more reading on the details, there is a reference that I think is pretty good. It's a patent that was issued back in 1987. It's called A Method and System for Employing a Push-Pull Liquid Crystal Modulator. Okay, I hope this helped clear up a little bit exactly how that does work. Have fun at the movies.